Welcome to our Maximizing LTE MIMO Throughput Using Drive Test Measurements webinar. First, before we get started, a couple of housekeeping items. We're going to put everyone on mute that is attending this webinar, but you will have the opportunity to ask questions. If you look at the box on the right-hand side of your screen, you should see a place to submit your questions, and we'll have a Q&A at the end of the webinar. Bruce?
Hello, I'm Bruce Hoffler, Vice President of Product Management for the RFS Business Area of PCTEL, and would like to welcome everyone to today's webinar titled Maximizing LTE MIMO Throughput Using Drive Test Measurements. I'd like to start today by looking at some projections associated with mobile broadband over the next few years. After that, I'll turn the discussion back over to Jim Zick, who is Senior Product Manager for PCTEL, with responsibility for the SeeGull scanning receiver product line. If we start off by taking a look at chart number 3, mobile bandwidth need, what we see here is that the Cisco Visual Networking Index for global mobile data traffic, published earlier part of this year, reported that in 2011, mobile traffic globally was approximately 0.6 exabytes per month. More importantly, though, over the next 5 years, this is going to grow to in excess of 10 exabytes. So over a 5-year period for global mobile data traffic, we're going to see an 18-fold increase. In chart 4, spectrum crunch, an FCC technical paper that discusses the benefits of adding additional spectrum predicted based upon 2009-2010 spectrum allocations that beginning next year in 2013, we begin to see a spectrum crunch, specifically approximately 90 megahertz of spectrum crunch. Now, if new spectrum isn't introduced and if more effective use of spectrum doesn't occur, this deficit is going to increase. So in 2013, we see a deficit of about 90 megahertz based upon projections. In 2014, that jumps to 270 megahertz in terms of the deficit. So the question is, how does the industry address these problems? The mobile bandwidth need as well as the deficiency in spectrum. And looking at the bottleneck or the solution to the air interface bottleneck, there's a couple of different methods that would need to be utilized. First, obviously, allocating more spectrum. Unfortunately, this is a very limited resource and a very expensive resource. Allocating more spectrum doesn't happen overnight. It's typically a 5 to 7 year ordeal. Wi-Fi offloading, another option. It's viable. Matter of fact, a number of carriers currently use Wi-Fi offloading, but it requires more infrastructure. Increased cell density. Again, added capital, added deployment costs, added maintenance costs. Finally, spectrum efficiency. And what we're talking about here is basically better use of the spectrum you have today. And this is involving the migration to LTE, LTE Advanced, and LTE MIMO. In today's webinar, we're going to look at LTE MIMO to help understand how this is going to alleviate the spectrum crunch and address some of the bandwidth needs. So the first question really is, why MIMO? And a couple very simple points. One is, moving to MIMO, it provides increased efficiency at a low to medium cost. And the primary reason behind that is most, if not all, base stations, LTE base stations, they're being rolled out today, have the MIMO capability turned on, or actually have the MIMO capability built in. Not necessarily turned on at this part, but built in. And the second point is, if we look at the physical layer, the graph at the bottom of page 6, we can quickly see that if we look at a transmit receive antenna pair of 2x1, we're seeing about 5 bits per second per hertz in terms of spectrum efficiency. As we move up from 2x1 to 2x2 to 4x4 to 8x8, you start to see that we can exceed 30 bits per second per megahertz or per hertz. So you see the efficiency increases significantly as the transmit-receive antennas increase as well. Okay, at this point, I'd like to turn the webinar back over to Jim Zick for today's topic, maximizing LTE MIMO throughput using drive test measurements.
Thank you, Bruce, and good morning to everyone, or good afternoon or good evening, wherever you may be in this world we all share. My name is Jim Zick, and what I first want to do is briefly explain what MIMO is, and then I want to go through the MIMO measurements that we think are important for testing your network, followed by a couple examples or case studies that we did on an outdoor DAS system as well as on a macro cell. And as Bruce mentioned, MIMO is going to be one of the key elements to be able to maximize throughput, even though all of those methods that were shown on a couple of previous slides will be employed by 2016 in order to be able to alleviate the spectrum crunch that we are going to be seeing starting in 2013. So shown here on chart 7, we have 4 different antenna schemes that are used in mobile deployments today. You're probably all very familiar with the single input, single receive antenna system, SeeGull, which is single output, single input, single output. And what input means here is input from the transmitter into the air, and output means output from the air into the receive antenna. And for some people that's a little non-intuitive, but this is how it's defined in the industry. So for simplicity, I'm showing the transmission only in one direction from the eNode B, the base station, to the UE. And what we show here are examples of what SeeGull is, SIMO, single input, multiple output, MISO, multiple input, single output, also known as transmit diversity, as well as a MIMO, which is the topic that we have today, multiple input, multiple output. MIMO is a smart technology that employs multiple antennas at both the transmitter and the receiver as shown here. It can be 2x2, it can be 4x2, which would be 4 transmitters and antennas and 2 receive antennas, 4x4, 8x8, or any other combination. 2x2 is widely deployed in LTE today, with both 4x2 and 4x4 emerging, actually being in some test networks today. With MIMO, multiple signals are transmitted on multiple paths, creating the possibility of improving spectral efficiency by improving throughput. But MIMO is more than just multiple inputs and multiple outputs, because it involves a technique called spatial multiplexing, which I'll talk about on the next slide. So how does MIMO really work? It employs a technique called spatial multiplexing, where multiple data streams are simultaneously transmitted on the same frequency and at the same time over different paths. The MIMO requires separate paths and also requires a very high signal-to-noise ratio to improve throughput. The most common antenna used for 2x2 MIMO on macro cells are the cross-polarized antennas, where you have 2 antennas that are oriented 90 degrees from each other, kind of in a crisscross configuration. But there are also other configurations where you'll have 2 antennas that are located parallel to each other by a small distance. So if you look at the diagram on the right-hand side, this is how spatial multiplexing works. Essentially, you have a code word that arrives from an unmodulated higher level process. And these code words, in this case we're showing 2, then move into step 2, where we have the scrambling and demodulation, or I should say the modulation taking place. Once the signal is then modulated, it gets put into a layer mapper, where it actually goes through a pre-coding matrix and now the layers are separated on two different streams. So for example, as you see there, we have layers 1 and 2 on one stream, and also layers 1 and 2 on a second stream. Then these layers are actually going through, and they're assigned to a resource block. And each one of these resource blocks, you have several resource blocks which are assigned to a UE. So in that example you see here, you may have like 8 or 9 resource blocks dedicated to UE1, and a smaller amount of UE blocks, or resource blocks, devoted to UE2, UE3, or UE4. So the next step is you go through the OFM signal generator, which then puts that signal out to the transmit antennas in step 6. And then once the signal on separate layers are going on separate paths through the air interface to the receive antennas, you are then receiving this signal at your UE, where the signal is combined from all the paths, decoded, and each code word is put out separately. It's essentially the reverse process that we saw in the transmit side that I had just gone through, steps 1 through 6. The next thing on slide 9 is to understand what the transmission modes are. So here we have the transmission modes that are defined by 3GPP. Modes 1, 2, and 7 represent non-MIMO based antenna techniques for LTE networks, where the UE or E node B does not support MIMO. Modes 2, 3, and 4 are single-user MIMO modes that represent the core of the LTE's downlink transmission techniques in current deployments. Now there is some debate whether transmit diversity mode 2 is really MIMO. Technically it's really not, because it's just transmit diversity, because it does not use spatial multiplexing. Modes 5 and 8 are transmission modes that include multi-user MIMO and beamforming that may be deployed sometime in the future, probably when LTE Advanced Release 10 gets deployed. Modes 8 and 9 were actually defined in Release 9. So the transmission modes you see here in the green arrows are the ones typically deployed today. Now with each one of these transmission modes, you can enable more and more throughput. So as you get more complicated into these transmission modes, you'll be able to get more throughput, but it also requires more signal processing. And kind of in the diagram on the bottom right, you see the most common modes, mode 2, 3, 4, and 6. And what we're showing here is that you have different feedback elements, or I should say mechanisms, from the UE back to the base station, which is why you're able to get more throughput when you go to different modes, such as mode 4, which would maximize your MIMO throughput of these 4 transmission modes that I show here in this diagram on the lower right. So let's move on to the next slide, slide 10, and really try to find out why we want to test MIMO. What are we really trying to accomplish by testing a MIMO network? So what we're trying to do is to determine the air interface's maximum throughput capacity for the different MIMO modes, essentially trying to find out what your MIMO gain is. And what we're able to do is to be able to provide the throughput gain of the physical layer for each transmission modes. So those transmission modes that I showed you on a previous slide is where we want to be able to determine what gain we have for each one of those modes. You know, the result is we want to be able to optimize the radio access network physical layer for maximum throughput by characterizing the link efficiency. We also have the added benefit of trying to be able to troubleshoot the RAN physical layer, to be able to isolate any path issues, and to be able to test for channel independence between the 2 antennas that we have mounted on the base station. So slide 11 is where we really get into what parameters are necessary for testing MIMO. The premise is that operators need to understand the MIMO transmission characteristics of the physical layer in the radio access network. So what this includes are a set of measurements that we think are very key for testing a MIMO network. One is path measurements, although path measurements aren't necessarily really MIMO measurements, because you can have path measurements with MISO or transmit diversity systems also. But they're a very key measurement to be able to understand what's happening on each path from your transmit to your receive antenna. There's channel quality indicator. This is also known as CQI, which is defined by 3GPP. The throughput number, which is very important for these data networks, LTE in particular, to be able to maximize the air interface throughput capability. And then the channel condition number, which we'll talk about all of these on the next few slides in more detail. Moving on to the next slide, RF path measurements. As you can see here, I have a 2x2 MIMO system set up in the diagram. And what we have is, since we have 2 transmit antennas and 2 receive antennas, we'll have 4 paths going from the transmit antenna to the receive antenna. So there's path 1-1 from transmit 1 to receive 1, path 1-2, path 2-1, and path 2-2. So all of these paths are important to be operating correctly in order to be able to maximize your throughput. What we're able to do with these path measurements is to determine if there's a problem with the base station port, a particular antenna, with regard to the MIMO paths. You know, whether it's an antenna problem, whether it's the cabling problem, or somebody misconnected the problem, or whether there's a port issue on the transmit base station. So the measurements that are provided are for each transmit-receive antenna pair. So as a result, we'll have 4 sets of measurements since we have 4 paths here for 2x2 MIMO. So these measurements include your standard LTE measurements, such as your reference signal received power, your reference signal received quality, and your reference signal CINR, or what some people call SINR, the signal to interference and noise ratio, or what we call the carrier signal to interference noise ratio, hence the CINR. The other important measurement is the channel quality indicator, as I mentioned previously. Because what this is it's a consistent indicator of the theoretical transmission physical layer efficiency. So if you look at this chart on the right-hand side, this was taken from 3GPP Technical Spec 36.213. We got the latest version here from September. And it matches the CQI index from 0 to 15, what the efficiency rate is for transmission in your air interface. So what you obviously want is a much higher CQI index, around 14 or 15. And as you notice, you have different modulation techniques with LTE, depending upon how far away you are from the base station. So if I'm with a CQI index of 1 to like 6, I'm with QPSK modulation. I'll have much lower efficiency, as shown in the chart. As I get closer to the base station with better conditions, I'll have 16 QAM. Or from 10 to 15, I'll have 64 QAM, which is really where you'd like to be, giving you the best efficiency possible for your air interface. So this is really an essential measurement tool for MIMO because with SeeGull systems, single input, single output, 1 transmit antenna, 1 receive antenna, your SINR or CINR translates directly to your CQI. There's a direct proportion, a direct correlation. So if you know what your CINR is, you can understand what your throughput is. However, with MIMO, CINR does not translate to CQI directly. So as a consequence, what you need is a CQI measurement, and this can be then used to be able to calculate what your throughput is based on these efficiency numbers that you see here in this chart. So on the next slide, slide 14, is where we talk about throughput. And what we're trying to do here with a scanner is to isolate the throughput of the radio access network. And this is kind of a complicated diagram. But as you look at the lower left-hand side, you can see where the physical layer is. And then you can also see where throughput is typically measured with the UE, which is the, across the whole network, all the way from the UE all the way back to your servers. So by physical layer, throughput, we are measuring the maximum throughput capacity that the RF environment will allow, which, what the air interface allows. UEs measure the total throughput of the RAN, including the backhaul, the server, which can be affected by a multitude of network devices, and the loading on these devices. So consequently, the user layer can be reduced by up to 10 times of what you see from the physical layer due to control overhead, handshaking, synchronization, retransmission, network loading, and so on. So it's important really, though, to be able to understand and take measurements from both the UE and the scanner. The reason being is you're able to isolate what your air input capability, your air interface capacity is with the scanner. And the UE actually gives you what the user is actually experiencing through the whole network. So based on the table from the previous slide from technical spec 36.213, we calculated the physical throughput based on the CQI number, which is shown in the chart here on the right-hand side. And this is shown for the common bandwidths of 5, 10, and 20 megahertz. And obviously, like I mentioned before, you really want to have high CQIs, which you typically get when you're much closer to the base station and you've really designed your network properly. The next item is the condition number. And the condition number is a measure of the independence or correlation of the channel paths. And this is measured in decibels. And what I have here in the chart below are some common industry norms for what you would like to see for a condition number. The lower the condition number is ideal. The higher the condition number is not ideal. So if you go through these numbers, condition number with a decibel number of 0, this indicates you have 2 totally independent channels. Really an ideal condition that can enable maximum throughput. If you're in the low teens, you have favorable conditions that can enable much better throughput than what a SISO or MISO system, base transmission system might be. If you're in the high teens, you have medium correlation, which can provide some marginal throughput, and generally if you're greater than 19 or 20, generally MIMO would not induce a condition that would increase throughput. However, despite of this industry norm, what I have here, we've done a lot of studies on this, and we're actually showing that even with high condition numbers, 20 or greater, 25, we're still seeing MIMO gain if you have very good CINR or SINR. But regardless, the condition number can really help you analyze some of the potential causes for throughput issues. But it's actually not really used in the calculation of the throughput itself. But it does allow you to analyze some of the problems that might be caused with your antennas as to how they're set up. Let's move on to the next slide, slide 16, and how you can interpret some of these MIMO measurements. And this is just a few examples. There are plenty more, but when you have the different measurements, such as the condition number, the ECQI, what I call estimated CQI, and the transmission mode measurements, it really allows operators to diagnose what the causes of low throughput might be. So for example, if you have a low condition number, which is a good thing, and low CQI, which is not a good thing, means you probably have a interference problem or a power issue, or you may just be very, very far from the base station because you have low power. High condition number and low CQI, again, this would not be ideal. High is not necessarily very good, and a low CQI, not very good. Means you have high channel correlation. You probably have low SINR or CINR. So it's something you want to be able to look at to be able to determine, what the cause of this might be. And there are plenty more examples which, once you understand how MIMO is actually operating, you'll be able to determine what are the causes of low throughput in the MIMO system. So some of the MIMO testing benefits are the ability to characterize the RF propagation for MIMO. So when you use a scanner, you get very consistent, repeatable RF data that's independent of the backhaul, the network layer overhead, or the server loading. You also have very high dynamic range to determine if you have where the noise floor is and any potential interference effects, as well as very good data density to be able to locate any fading issues or any areas where you have reduced MIMO throughput. You also have the ability to determine the channel independence with the condition number, to be able to analyze network problems related to multipath conditions, and to be able to understand how antenna tilt or relocation can affect throughput. And with a scanner, you can also provide various transmission modes to be able to understand how different transmission modes affect RAM performance and throughput performance. So if I want to be able to go to mode 4 and I have that implemented in the base station, I should be able to get better throughput than I would with maybe a mode 2. And then also to be able to troubleshoot any antenna or cabling issues or base station ports, using the path measurements. So with the scanner, you have a lot of ability to test what's happening in your radio access network that you might not get with the UE. But however, a UE is also very important to be able to understand what the user is actually experiencing in the network. So with that, what I'd like to do is actually go on to some examples and case studies that we've done using these measurements to be able to give you a clear idea of how MIMO measurements can be very, very important to testing your MIMO network. We'll also be taking questions at the end of the webinar here. So if you want to be able to, if you have any questions in mind, please send them in and we'll answer them at the end of this webinar. We'll have about a 10 or 15-minute question and answer period. So moving on to slide 18, this is a MIMO outdoor DAS case study that we did. And in this case, it was a LTE FDD network, 2x2 MIMO. We did this last April. And in this case, the outdoor DAS system, the reason why it was deployed is there were cell tower restrictions. So as a result, we were forced to put in an outdoor DAS system in this particular area. One of the unfortunate things, though, was this area was characterized by very high foliage and low antenna height because they had to put the antennas on top of the utility poles. So essentially, they had the antennas sticking right amongst the foliage in this particular example. If you look at this chart here, all these little red dots are where the antenna locations are. So we did a drive test of this, and we did this, if we move on to the next slide, we did simultaneous testing with a scanner as well as with a UE data card. So in this case, we used a PCTEL SeeGull EX scanner, as well as a MIMO test data card on another system. And we wanted to find out what the difference was, first of all, not only to test the system, but also to find out what the difference is in the result of a scanner as well as a UE, so you can really be able to understand how a MIMO system works. So we did an orientation test with the UE. We did a walk test versus a drive test. We also are looking at all the MIMO transmission modes on the scanner. And then we looked at the various parameters like RSRP, condition number, your CINR and throughput numbers. So first, why use a scanner? Somebody might ask if you have a UE. Well, if you look at this technical report from 37.976, and this is directly a quote from this technical report from 3GPP, is that they state that 3GPP already defined conducted tests for MIMO and multiple antennas. But it's clear that the ability to duplicate these gains in the field is highly dependent on the performance of the receiver antenna system. But they also mention here that MIMO over-the-air throughput is measured at the top of the physical layer of an HSDA or an LTE system. So with a scanner, you're able to measure according to what this technical report recommends, because a scanner uses omnidirectional antennas. And they also measure throughput at the physical layer. And then they also provide the throughput of the multiple MIMO transmission modes. Instead of like a UE, it'll only provide the throughput of the transmission mode that the UE is locked onto. So let's then move into some actual details of this case study on the next slide. So in this case, we did an orientation analysis of a UE data card. We positioned it at position with 0 degrees. And then what we did is we rotated the laptop by 90 degrees. And as you can see, the throughput of the system changed drastically. We had 2.8 megabits per second on an average if you take all those data points that you see in position 0. And then if you take the average of all the data points in position C, because we also had a position B where we did 45 degrees, but you can see that between the maximum and the minimum, we had about a 2.3x difference depending upon the orientation due to the directionality of the antennas, of the UE antennas. And this was a stationary test. We just did this in position. The reason for this is MIMO antennas and UEs, because of the way they're designed and having them fit in the packaging that is required. They're very typically directional and can have some constraints on them. The next thing we did is we also did a speed analysis. So as part of the drive test that we did, we went down to one city block and we did a UE walk test, and then we also did a UE drive test at 20 miles an hour. So with the UE walk test, we're walking at about 3 miles an hour. With the UE drive test, we were operating the vehicle at about 20 miles an hour. And again, as you see here, you see a huge difference in the amount of throughput that you have based on the walk test and the UE drive test. So on the left-hand side, on the lower left, see a lot of data points, anywhere from 1.5 megabits per second all the way up to about 4.5 megabits per second on the walk test. But as soon as we started moving the vehicle at about 20, 25 miles an hour, a lot of the data points dropped to about a half of megabit per second to 1 megabit per second. So on the average, the UE dropped by over 2 times with the drive test. And again, the scanner was not affected by this. Whether we did a walk test or a drive test, same with the orientation. We really didn't have any difference between the orientation of the vehicle when we have the 2 antennas on top of the car roof. So moving on to the next slide, slide 23, here's where we actually show the drive test data. So on the top we show the UE data, and on the bottom we show the scanner data over a certain section of what we had tested. And as you can see, actually on the east to west test, the UE data and the scanner data correlated quite nicely, although the throughput was overall very low, whether it was the UE throughput or the scanner throughput. They did correlate, and one thing you might notice, though, is that, again, the throughput on the scanner will be a lot higher because we're measuring, again, at the top of the physical layer versus a UE, which is measuring through the backhaul, through the server, as well as the air interface. And you have all the handshaking and all the network loading going on with the UE. But regardless of that, you see that there's good correlation there. But as soon as we did the north-south test, you see that there's very, very poor correlation. And we believe this had to do with the orientation of the UE, of the data card, when we turned the vehicle in the north-south position. So consequently, we did not see the correlation that you would like to see between the scanner and the UE as you change position of the vehicle. So then what we did is we looked a little more at the scanner data, And here's what we're trying to do is we're trying to compare, this is slide 24, we're trying to compare the transmission modes of transmit diversity mode 2, which is technically really not MIMO, but it's deployed in a lot of cases. And then with mode 4, which is the maximum amount of throughput you can get of those transmission modes that I showed on slides previously. And what you see here is when you look at the gain, the throughput gain between transmit diversity and closed loop spatial multiplexing, you look at those bar charts on the bottom, you essentially don't really see a large difference. In fact, you see virtually no difference between transmit diversity and closed loop spatial multiplexing. So what this tells you really is that you're not seeing any MIMO gain in the system. It's not really helping you having a MIMO system here with spatial multiplexing over what you could do with just normal open loop transmit diversity. So then we looked at the RSRP numbers, and if you look at the chart on the bottom, you see a lot of data points in the -115, -100 range. It's very marginal. You really want to see a lot of your RSRP in the -70, -80, maybe some of the -90 range. So you have pretty weak RSRP in this particular system that was deployed. We then looked at the, on slide 26, the CINR as well as the, what some people call SINR. And again, we're showing very poor CINR results. A lot of data, if you look at the bar chart on the bottom, in the -10 dB and 0 range, you really like to see a lot of your results being in the 10 to 20 decibel range. So in both cases, in this case, what we're seeing is for both RSRP and CINR, we're on the low end for this particular system. We then looked at the condition number, and the condition number, you really want to be, in the mid-teens or below. And we're actually showing decent condition number here, which means the antennas are deployed properly in a sense where you're not getting a tremendous amount of correlation. You really want to have very low correlation, and we're showing that we have low CN, which is a good thing. And as a result of that, at least the antennas are deployed in a situation where you would have a possibility of having high MIMO gain. But as we know, MIMO really requires high CINR, and we did not have high CINR. So as a result, you're not really seeing any MIMO gain in the system. So in this case study, the conclusions are that MIMO is really ineffective in this network. The network has a severe interference or noise problem, very marginal RSRP, and very poor CINR. However, the conditions are favorable for MIMO to improve throughput because you have a low condition number. And the other thing we concluded is if you're looking at the UE for MIMO, you really have to carefully examine the results you get, since they're affected by UE orientation, the speed of the movement of the vehicle during the test, whether you do a drive test or walk test for outdoor systems. And we're also able to, the UE also locks on to the transmission mode that it's actually connected to in the session. So as a result, you're not going to be able to understand what all the different gain is for the various transmission modes in the system. So the conclusion here is a scanner is very effective in characterizing the MIMO network. Again, a UE is important, so you understand what the user actually experiences. But it's not very valuable in actually characterizing the network. So now we're going to move on to a macro cell case, and this we did about 11 months ago. This was done in an outdoor network, again, a macro cell case in Baltimore, and this was in downtown Baltimore. So it's a very urban environment with high-rise buildings. And what we have shown here in the picture are a lot of what we have here shown here is a lot of PCIs. What we're going to analyze here in the center of the diagram is actually one PCI, which is what the best server would be for that region. So we can really understand what's happening for that best server with regards to what MIMO can do. So first we looked at RSRP, and this is slide 30. And if you look at the RSRP, we have very, very excellent RSRP. If you look at that center of the chart where I have that part of it circled, you're seeing RSRP measurements in the range of as high as minus 60 to minus 50 dBm, and pretty much only on the edges you see anything that's down around minus 90. So this system has excellent RSRP for the best serving area that it's addressing. So we then, on the same drive test, we looked at some of the MIMO measurements. So we looked at transmit diversity versus mode 4 for the transmission mode. So if you look at doing just transmit diversity, which is mode 2, technically not really MIMO, we're actually seeing throughput in the range of anywhere from 16 to 48 megabits per second. Again, this is very high because we're measuring at the physical layer, at the top of the physical layer. But when you go to MIMO transmission mode 4, which is your closed loop spatial multiplexing, you're actually seeing quite a bit of improvement in the throughput, anywhere from, in some cases, as high as 64 to 80 megabits per second. But you're also seeing a lot of numbers in the anywhere from 16 to 80 megabits per second. So if you're able to operate in transmission mode 4, you're going to get a lot of MIMO gain in this particular serving area. So if you look at slide 32, we actually did a delta. So what we did is we subtracted off the transmission mode 4 closed loop spatial multiplexing from just doing plain old transmit diversity. To look at what the throughput is if you're using transmission mode 4. So your actual throughput here in the best serving area would range at the top of the physical layer, and this is your maximum capacity of what the of your throughput could be, is all the way up to 40 megabits per second gain over transmit diversity, down to about maybe 2 to 5 megabits per second as you get towards the cell edges. Now, one thing that you may notice here is that if you get outside the best server area, you're in the pink region. You see a lot of pink there, which is actually negative gain, because you have negative, anywhere from minus 2 to 0 megabits per second. And the reason for that is because you have very low CINR. Your transmit diversity can actually be a little more efficient than MIMO. However, you really don't need to worry about this because the UE would have already locked on to the best transmission mode and to another server. But it is something that a scanner can tell you and show you what benefits are of MIMO and where they might not be beneficial if you happen not have any best serving areas that encapsulate this particular cell. So then what we did is we looked at the MIMO condition number and the CINR. And on the left-hand side, you can see that we have a condition number that's pretty decent until you're right in the middle, that exact center where you have very high CN. But if you noticed on the previous slide, we also happen to have pretty high MIMO gain there also, which you would think would be not necessarily the two conditions you'd want to have maximum MIMO gain. So we did then is looked at the CINR also in the very center here and found that we had very, very good CINR. So what this is telling us is that even if you have a high condition number, if you have very excellent CINR like we have here, you can still get MIMO gain. And those industry norms that I showed on that slide, about 7-8 slides back, you're not necessarily, you don't necessarily have to follow those industry norms that we showed. So to summarize these, this whole MIMO webinar, as well as these case studies that we did, is we found that MIMO was very effective for maximizing throughput in the Baltimore macro cell case study. And MIMO was not really effective in the ODAS case study, and whether that's due to a suboptimal design, how it was deployed, and probably most likely because of the terrain with the high foliage, it was really not effective in that particular case. And this is what a scanner is able to tell you. So the benefits of testing with a scanner is you're able to characterize that RF propagation for MIMO with consistent, repeatable RF data independent, that's independent of backhaul, the network layer, the overhead, and the serving, and the server loading. You have a high dynamic range to determine the noise floor and any potential interference effects, as well as good data density for locating fading issues and where you might have reduced MIMO throughput. You can also determine the channel independence with your condition number and understand how antenna tilt and relocation may affect the throughput. You can look at the different transmission modes. In the case, what I did in these examples is I looked at modes 2 and 4, transmit diversity, as well as closed loop spatial multiplexing. But you can also look at the other transmission modes, mode 6 and mode 3, your open loop transmission modes. And you're also able to troubleshoot any antenna or cabling issues, as well as any TX ports on the base station with your path measurements. So I hope this webinar has been very informative. We're going to move now into the Q&A part of this webinar. I want to thank everyone for joining. And I also want to let you know that we have an LTE MIMO poster if you're interested. This is a 26 by 36 inch size poster, which goes through really what MIMO is all about, what measurements are important. And if you log on to our website here that's shown, you're able to put in your registration information, and we'll send you a MIMO poster. So with that, we're going to start taking questions now, and we have quite a few of them from what I see here on our system.
Yeah. Okay. First question we have is, how do you place antennas when testing MIMO with a scanning receiver?
Yeah, that's a good question. As you know, with the UE, your antennas are pretty much set inside the UE. But with when you're trying to test with a scanning receiver, you typically put them on a rooftop, and you want to be able to separate them by about 2 lambda, so you don't have any field effects affecting one antenna affecting the other. So, in the case of, as you get closer to the 2600 megahertz range, you probably want to keep them only, I don't know, anywhere in the neighborhood of maybe 5 or 6 inches apart. But if you're down to 700, you want to be a good, 15, 20 inches apart. But it's important to keep them apart because each one of those is a separate path in the MIMO system. So consequently, you're taking measurements from each path of the transmit base station to each one of those antenna receivers that you have.
Was the transmit imbalance issue taken into account when considering the MIMO gain for the macro tests that we did?
Yeah, I'm not sure. When you talk about the imbalance, we were able to see very good path measurements on each antenna path with this particular case. So we really didn't have any imbalance when we were able to do this. Now, obviously, when you get towards the edges, you start to see one of the paths or 2 of the paths trying to having lower RSRP. And yes, that is taken into account when you see that when we did the drive test, and that's shown in the data that we have.
Okay. We've got a second antenna question here. Basically, you've talked about the placement of antennas. The second question here asks, do you need any special antennas for testing MIMO?
Not really. I mean, we use the normal omnidirectional antennas because if you look at that technical report that 3GPP stated that you really want to have omnidirectional antennas to be able to understand what your over-the-air interface is like with regard to MIMO throughput. So using standard omnidirectional antennas, spacing them apart so you don't have any field effects between them is really all you need to test a MIMO system. In an indoor case, you obviously can't necessarily get that separation, so you typically angle them at about 45 degrees from each other. And since you're in a reflection-rich environment, you're fine for testing MIMO.
Here's a question associated with indoor MIMO. Is there a way of testing MIMO indoors before deployment to determine if MIMO is cost-effective?
That's another very good question. Typically, we say MIMO is a low-cost way of getting better spectral usage or spectral efficiency. And that's kind of true for outdoor systems, but when you get to indoor systems, the problem with MIMO is the installation cost of that indoor system is usually a very large cost of the installation. So the question I think he's really asking here is there a way to determine whether MIMO is effective in an indoor environment so I can know whether or not it's worth my cost of putting that MIMO system in. And the way to do that really is to be able to, when you set up your system, typically when you first are trying to deploy a cell, you put a continuous wave transmitter up. The only way of really doing this for MIMO would be to actually put up a transmitter that is a MIMO transmitter, I should say an LTE transmitter, that is broadcasting MIMO instead of a continuous wave one, and then you would be able to do that. But I understand that not many people probably have that capability, but that would be the only way of really determining whether MIMO would be effective.
All right, we have another question here about the effectiveness. If I test MIMO and find out it's not effective, how can I optimize it?
Another good question. Some of the ways you can do that is to be able to adjust your antenna tilt or azimuth would be one way. Again, that is probably very labor intensive. Another way is like if you saw in that ODAS system, if you look at it kind of at the 30,000 foot level, probably what's happening there is you're getting interference from other cells. And one way of combating that is probably, and you also have low CINR, so in that particular case what you might have to do is to maybe turn up the power on some of the base stations and maybe turn off some of the other antennas or possibly reduce the power on those. So you're able to get better RSRP and CINR. Again, this is can be an arduous process, but probably an important one if you have very low throughput.
Thank you, Jim. Another good question here. Are path measurements and MIMO measurements the same?
Technically, path measurements aren't really MIMO measurements. They're only looking at the path between the transmitter and the receiver. And you can have those path measurements in the case of transmit diversity where technically it's really not MIMO because MIMO technically is really spatial multiplexing. So no, they're not technically really MIMO measurements, but they are very important measurements to be able to determine if you have a problem with one of the paths in your system, whether it's MIMO or non-MIMO.
Thank you, Jim. I think that's all the time we have for the day's webinar. I'd like to thank everyone for participating. A couple of points before we sign off. First, the charts that Jim stepped through today we will put on the PCTEL website for downloading by everyone. Also, we will put a version of the actual webinar up on our website as well. Finally, if there are any other questions after the conclusion of this webinar, please feel free to submit them to rfs.marketing@pctel.com. Thank you very much for your participation.